Hello, everyone, and good afternoon. We have the pleasure today to have as speaker Dr. Bushra Khaled Alarfaj from the Department of Statistics and Operation Research of the King Saud University. Dr. Bushra gives us a talk with titled The Joint Node Degree Distribution in the Erdős-Rényi Network. Thank you again, Dr. Bushra, for accepting to speak in our webinar, and please, you can start.
Thank you very much. Hello, everyone. First of all, I would like to thank Dr. Rafiq Agash for inviting me. And I also want to thank the audience for being here. I hope you enjoy my talk today about the joint node degree distribution and the Erdős-Rényi network. To begin, I would like to introduce myself. I'm an assistant professor at King Saud University, and I earned my PhD from the University of Leeds in the UK, and my master's degree was from the University of Manchester. My main areas of interest are statistical learning, data mining, complex network analysis, random graph models, and spatial statistics. I will begin by giving some basic ideas about what a network is and why the study of networks is important. A network consists of distinct elements represented by nodes, or we call them vertices, and the connections between these elements represented as links or edges. Why network science is important? The study of networks has emerged in various applications as a means of analyzing complex relation data, such as transportation networks, biological networks, and social networks. In transportation applications, such as a network of direct flights around the world, we may be interested in solving complex phenomena, such as which airports are at the highest risk for virus spreading. Another example is in biology, specifically protein-protein interaction networks. We may be interested in answering the question, do proteins interact with each other? In social networks such as Facebook, which display friendship networks where the nodes are people and the edges are relationships, we may want to know who the most influential people in this network are, for example. All of these examples involve complex phenomena, so if we can represent them as networks, we can better understand these phenomena by studying the structure of such networks and using certain statistical methods. Actually, there are many examples of networks around us, like social media networks, brain networks, information technology networks, and transportation networks. Now I'm going to talk or give a background of the theory of random graphs. The theory of random graphs has emerged as a distinct field within discrete mathematics. It arises from the introduction of probabilistic methods in graph theory. So we can say that random graph theory lies at the intersection of probability theory, combinatorics, and graph theory. We can define a random graph or random graph model as a set of nodes and edges in which some pairs of nodes are connected by edges at random. And we can categorize random graph models into two classes, static models and dynamic models. There are two types of static models based on the topological properties they provide, which are random models and small world models. For dynamic models, the most commonly discussed type in the literature is the preferential attachment model. Examples of random graph models include the Erdős-Rényi model and the configuration model, which is a generalization of the Erdős-Rényi model. And examples of small world models are the Watts-Rogetz model and the Newman model. And one example of a preferential attachment model is the Barabasi-Albert model. Now let's go over some basic concepts in network science and the graph theory. As mentioned earlier, a network is a collection of nodes connected by edges. You can see here a simple example of a network with 4 nodes and 4 edges. In this example, each edge has 2 nodes called endpoints that it connects these 2 nodes or these 2 endpoints. If 2 or more edges share the same endpoint, the graph is said to have multiple edges. Additionally, an edge that connects a node to itself is called a loop. If a graph has neither multiple edges or loops, it is referred to as a simple graph, which is the type we will study. If the edges in a graph don't have a specific direction, we call it an undirected graph. In our study, we only consider simple and undirected graphs. Another important concept is the degree of a vertex V, which is the number of edges connected to V. So, for example, in this simple graph, we can see that there are 3 edges connected to the node V. So we can say V has a degree of 3. Now we introduce the Erdős-Rényi model. The Erdős-Rényi random graph model was proposed by Erdős and Rényi in 1959. And this model is denoted as the GMP model. And the Erdős-Rényi model, each pair of n nodes is connected with a probability P. So the degree of a single node in the graph follows a binomial distribution, which is why this model is sometimes referred to as the binomial model. So the model has 2 parameters, n, which is the number of nodes in the graph, and b, which is the probability of an edge presence in the graph. As we can see in these simple networks, when we use a small probability, there are few edges in the graph, and when the probability p increases, the number of edges also increases. It is clear that the node degree distribution for a single node in an Erdős-Rényi network follows a binomial distribution as given by equation 1. Why we use n-1 here instead of n? Because for a particular node, there are n-1 other nodes that can be connected to it.
So every node cannot be connected to itself.
Yeah, because if the node connects to itself, it's called a loop. And we discuss here a simple network which doesn't have loops or multiple edges.
Okay.
We know the degree distribution for every node in a graph, which is binomial distribution, but this is independently this distribution is independently for every single node in a graph. However, the degrees of the nodes are not independent, as an increase in the degree of one node implies a corresponding change in the degree of another node in the graph. So this fact has motivated us to investigate the joint node degree distribution. Also knowing that the binomial distribution can be approximated by a normal distribution using the central limit theorem, for a certain values of parameters. So we want to test the multivariate normal distribution as an approximation to the joint node degree distribution in the Erdős-Rényi network.
Sorry, in the previous slide, what means minimum of NP and if you can go to previous.
Here.
Before.
No, here.
Yes.
Yeah, this one.
What do you mean by minimum? What represents minimum of NPN multiplied by 1 minus P? Why this condition? Why you use it? Where we use this condition?
To use the central limit theorem, we need to have either the minimum value, yeah.
Okay. The critical value of N and P to can approximate the binomial by
this is the
central
condition.
Normal distribution. Okay, thank you.
Yeah, to approximate binomial to a normal.
Okay.
So since we can use the normal approximation to the binomial distribution for each single node in a graph based on the central limit theorem, we will test the multivariate normal distribution as an approximation for the joint degree distribution in an Erdős-Rényi graph. This will be conducted using computational methods, and this is one part of the study. Another part of the study is to investigate whether we can ignore the dependence between degrees in a graph under certain conditions. So to test the multivariate normal distribution, we first need to calculate the covariance and correlation between degrees. As you can see, the covariance is not equal to 0 and depends on the value of P, which ensures the dependence between degrees. Now we will test the multivariate normal distribution under two cases. First, if we ignore the dependence and set the covariance to 0. Second, if we consider the dependence and set the covariance to the equation we calculated, which is P times 1 minus P. We will also consider two methods when generating simulated Erdős-Rényi graphs. Method 1, when we use the actual value of P that we used to generate the graphs in order to calculate the mean vector and the variance covariance matrix. Here, the mean vector mu and the variance covariance matrix sigma. And the second method, when we use the estimated P from each generated graph to calculate the mean and sigma, which may enhance the goodness of fit when we use estimated P rather than actual P.
You obtain P hat, please. So, how you obtain P hat? P hat, the estimate of P.
When we generate a graph, we estimate P hat from the generated graph by counting how many edges in the generated graph and divide this number by the total number of possible edges.
Okay, thank you.
We will use the following tests for goodness of fit: the chi-square goodness of fit test, the Anderson-Darling test, and we will also assess how close the empirical cumulative distribution function CDF of the observed statistics is to the theoretical CDF by evaluating the sum of squared differences between the CDFs. We compare the proportion of rejected statistics for various values of N and P to the 5% threshold. So the first figure when we use actual P, the solid lines represent the result assuming independence between node degrees when we set covariance to 0, while the dashed lines represent the result assuming dependence when the covariance equals to P times 1 minus P. And also in these tables, we can see the results we obtain for various values of P and N when we use a small n, a large N, and also small p and large P. The tables display the proportions of rejected statistics associated with the specific values of N and P. So in this table, we can see the results for the independent degree case with actual P. Here, the dependent with actual P, and here, independent degrees with estimated P, and this table for dependent degrees with estimated P. We achieve the best fit when 50 out of 1,000 statistics are rejected, since we use 1,000 simulated graphs. And for each graph, we do the test. So when we achieve, when we reject about 5% of this 1,000%, we accept the hypothesis as the significance level is set at 5%. By comparing the proportions of rejected statistics at a significance level of 5%, we observe that we consistently achieve a good fit for the multivariate normal distribution with large values of N, and specifically when P equals a half. Also, I want to say that the approximation appears to be valid when N times B is greater than or equal to 10. And all 4 cases show similar results. However, the case that use the estimated value of P and assume dependence between degrees when calculating the statistics demonstrate slightly better performance. Another part of the study is to compare the independence and dependence cases. We calculate the maximum likelihood estimate of the probability of an edge presence in the graph P. Once for the independence case when we set the covariance to 0, and another time for the dependence case when we set the covariance to P times 1 minus P. Obtaining equation 4 involved complicated and lengthy steps, resulting in a cubic equation that is difficult to solve for P. Therefore, we approximate the solution by omitting the cubic term and solving the resulting quadratic equation, yielding equation 5. So since equation 4 is hard to be solved, we omit the cubic term, solve it for the quadratic equation, and we approximate it again here in equation 3 after omitting all the unnecessary terms. Similarly, for the dependence case, we approach the dependence case, which is slightly more challenging to calculate compared to the independence case. So here in the dependence case also we can see in equation 7 it is a cubic equation and it is very hard to be solved. So we solve it approximately. First, there is a missing slide. Yeah, first when we omit the cubic term and solve it for the quadratic term, and second, we solve it approximately when we omit all the unnecessary terms. We then compare the two estimators, equation 4 for independence and equation 7 for dependence. Because equation 4 and equation 7 are cubic equations, so we use the function uniroot in R. So we can find the value of P using this function. When comparing the two cases, we use very small and large values of n to assess the estimates of p as shown in the first column of the figure and to evaluate the biases of the estimates as depicted in the second column. We have noticed that regardless of the value of n, when p equals 0.5, the two estimators exhibit very similar bias values. However, as n increases, the estimates concentrate around their mean, and the difference, which I mean by the difference is that smaller bias diminishes with both cases biases approaching zero. So we have demonstrated computationally that the multivariate normal distribution is a good approximation for the joint node degree distribution of the Erdős-Rényi model when n times p is greater than or equal to 10. And we show that as n increases, the difference between independence and dependence diminishes because the dependence between degrees becomes very weak. So with large values of n, we can ignore the dependence between the degrees of nodes. Thank you for your attention. Do you have any question?
Thank you for this nice talk, Dr. Bushra. Are there some questions, please?
Yes, please. Okay.
Wa alaikum salam.
Thank you for the presentation. I have a small question. In the second last slide, when you are comparing the bias of the estimator, won't it be a good idea to compare the variance as well at this point? Because sometimes we may have a very small bias, but the variance is large. So instead of having the bias only, why not we have a mean square error? So we can have like a trade-off between the bias and variance.
Yeah, that's right. We actually compared the variance and also the mean square error of the two estimators, but we don't recognize any difference between them. So this is why we only focus on the bias. The bias shows the difference, so we can decide when we can ignore the independence of degrees.
Okay, thank you.
Assalamu alaikum.
Salam alaikum.
I mean, how did you decide to remove the unnecessarily terms, the cubic and the other one? I mean, why you remove them? And how did you know they are unnecessary terms?
we use some theorems of limitations for large values of n. We use some rules of limitations to know which terms are unnecessary.
Okay, thank you.
Good evening. Assalamu alaikum, ma'am.
Assalamu alaikum. Hello, doctor.
I have a question that from the first slides you discussed about the social networks with respect to graph theory. In my master degree, I studied the subject graph theory. In fact, my thesis was about the chemical graph theory. I worked on different chemical structures like malum chain, borrophane chain, boron triangular sheet. I computed the Zagreb connection indices and modified Zagreb connection indices with respect to topological indices. I just want to know that how can we use the degree-based or any topological indices in social networks? When we take the chemical graph, we have a specific structure like n equals 1. If we are choosing a structure in one dimension, let's say we have a triangle. It means there are 3 vertex and 3 edges. And we are connecting another triangle with additional 1 edge. It means there will be 6 vertex and 7 edges. Similarly, in third dimension, n equals 3, we are connecting 3 vertex and with 1 edge, then 9 vertex and 10 edges. 3, 3, 6, 3, 9, 11 edges.
Mm-hmm.
My question is that in this type of structures, we know that this is first dimension, this is second dimension, this is third dimension, but you are discussing here social networks. It means how can we take a specific structure like this will be the first dimensional structure and we will be applying their degree-based topological indices or degree-based indices, and how we will be computing what will be the final outcome with respect to the degree-based topological indices when we will be applying these indices on social networks.
What do you mean by degree-based? You mean what do you want to do with the degrees? Not degree distribution, you mean?
Yes, I mean to say like a triangle is a 3 persons which are connected to each other. It means each vertex has degree 2. Each person is connected by 2 other people. Like
this, yeah.
how
This
yes,
type of graphs, yeah.
Yes,
This
please.
type of graphs are called regular graphs when where every node has the same number of edges or same number of degrees. It's called regular graphs, and this is this has I mean its own study.
Okay. I mean to say when we will be selecting or choosing any social network, let we take a network of Facebook. There are many persons which are connected by different people. Can we apply the graphical technique or degree-based technique on this type of network?
Yeah, you can. Because this type of data can be represented by a network, so you can it depends on what you want to do with this network.
Okay, thank you. It means whenever we have needed to find the connections between the specific individuals, we can use the graph theory. Thank you very much.
No problem. Thank you.
Thank you, Dr. Muhammad. Are there other questions, please? So I have a question.
Yeah.
For your estimator p hat, have you some asymptotic properties of p hat? Some almost surely convergence in distribution. What is the behavior of p hat of your estimator?
It is very close to the actual P we used
Why?
to generate
Why?
the graph.
This is the real question. Why it is very close? And it is very close in almost
When
surely or very close in distribution or what? Okay, very close, almost surely. Why it is very close to P? And what is the asymptotic distribution of P hat? Because P hat is an estimator, some random variable. So it has some asymptotic distribution.
Mm.
What about the asymptotic properties of P hat? For example, why P hat is very close to P? And why? What do you mean by very close? What is the rate of convergence of P hat to P?
Because when we use the actual P, this gives the probability of an edge we have in the graph. So when we estimate P by counting how many number of edges in the graph to the total number of all possible edges, yeah, the values will be very close to the.
Okay. And where you have used the asymptotic, the central limit theorem, where you have used the normal distribution, the approximation of the binomial distribution by normal distribution, where you have used this result, for example.
We say here the node degree distribution for.
Okay, is
for
a
a
normal?
single, yeah, it's binomial. We give it the notation x. So x is the number of degrees for a given node, and x follows binomial distribution. And here, x is a vector of n-dimensional random variables of degrees, each of which has a normal approximation to binomial.
Okay.
So we use it here.
Okay. If you can go to the equation 4, please. Equation 4 and 5.
Yeah.
Okay. And how you can resolve approximately this equation? The techniques that you have used to obtain an approximation of the solution of equation 4.
Yeah, equation 4 is a cubic equation.
Okay.
So we first, to have equation 5, we just omit the cubic term to be cubic.
Why?
Because it is unnecessary terms when n is large. When n goes to infinity, this term becomes unnecessary, goes to 0. So we can just omit it and solve the rest, which is a quadratic equation.
Okay, and we cannot do best than yes.
And we will get the positive root because P is a positive probability.
P must be between 0 and 1.
Must be positive, yeah.
Why P in equation 4 is between 0 and 1? It is not clear for me. Why it is necessarily between 0 and 1? Because it is a probability. So
it is a probability.
It must be between 0 and 1. Why the right-hand side of equation 4 is between 0 and 1?
The right-hand side?
Of equation 5, sorry, of equation 5. Why it is between 0 and 1?
It is a probability. It must be between 0 and 1.
Yes, this is the region. But why you confirm that the solution given in equation 4 confirms that P is a probability. So it must be between 0 and 1.
You mean why we use this root?
Yes. We are sure that this value in the hind side is between 0 1.
Yeah, I confirmed this result also numerically.
And please, what is the difference between small and capital N? What represents capital N?
Capital N is the dimensional, and it is equals to N.
Capital N is equal to small n?
It's equal to small n, yeah.
So why you
We
use...
just want to distinguish between the dimensional and the number of nodes.
And the small xi, what represents?
But the dimensional must be equals to the number of nodes.
The dimensional of what?
Here, I change it here, but I don't change it in the equations. Here,
Okay.
for example, sigma, it must be n capital times n capital, non-singular positive definite variance covariance. So it is the dimensional of the matrix, covariance matrix, and
Okay.
also the dimensional of the vector mu. So also here, it should be n capital, but I change it here to n small because they are equal. The dimensional equals to the number of nodes, but I didn't change it in the equation. Sorry.
Okay, no problem. And what sorry, there are some noise.
Same slide.
Yes, same slide, please.
Yeah.
No. After the slides where we have where we have equation 4 and 5.
Okay.
Okay. What is small xi here? Small xi, what represents?
The degrees.
Small xi, degrees.
Yeah.
The degree of node I.
Of node I, yeah.
Okay. And the degree is a random variable. Okay?
Yeah, it is a random variable.
Okay. So when n is large, xi, not n is large, because we have a random graph. So xi is a random variable. We cannot use the strong law of large numbers or weak law of large numbers to approximate summation of xi divided by n by the mean of xi by the mean of the node degree. It is possible or no to obtain a simplified expression of equation 4 of P. I think that summation of xi divided by n goes to some x dash, some small x dash, which represents the mean of the node degree. And the mean of node degree is
yeah, you mean
xi has binomial distribution. It's okay?
You mean we can more approximate it?
Yes, xi has binomial distribution. Yes or no?
Yeah, all of them can be approximated to this equation, sigma xi divided by n times n minus 1.
No, I think that this will goes to 0. Xi has binomial distribution with parameters np.
Yeah.
Is true or not? Xi, small xi, has binomial distribution. Here, for example.
Yeah, but we approximated to normal.
Okay, no. We use the binomial distribution. So summation of xi divided by n goes to p. So here we have also p, maybe. Okay. Dr. Burhan, you have a question? Burhan Halawani?
Yes, you said that xi are the degrees of the knots. And we know in the graph theory, the sum of all degrees of the knots is equal to the twice of edges of the graph.
Right. Yeah.
This is for regular graph.
For all graphs, regular
or simple graphs,
or simple graph, or so there are a relationship here with the number of edges and the number of vertices, capital N, you say it. And the approximation, Rafiq, when n is very big, You know that the binomial or approximate to the normal.
Yes,
Yeah.
yes,
Goes.
yes, yes.
We can do with with this aspect. We can prove. I think that p between 0 and 1, of course, in this equation. Just this.
Okay.
Thank you for.
Thank you, Dr.
slides.
Burhan. Thank you,
Dr. Rafiq.
Yes, Dr. Nish. تفضل.
Thank you. I have two questions for Doctor. First question, is really P independent of N or not?
P independent of N?
Yes, really or assumption, just as assumption from you.
Yeah, I think, yeah, P is independent of N. N is the number of nodes in the graph. P is the probability of edges present in the graph.
If N increase, P don't change.
Yeah.
It's constant for any graph.
Yeah, P doesn't change even if P doesn't change, but maybe the number of edges in the graph will be changed.
Because if it change, all approximation have no sense in this case. We know that in binomial P must be constant.
P is constant, yeah. P is constant here. This is why we
Just
report.
assumption or really, I don't know. I'm not expert in graph theory, but question, clarification.
I think that in her model, P is free of N, not depends on N. But in practice, I think that in social network, if we are 1,000 persons, the connection between two persons, the probability to that two persons will be connected depends on the number of persons.
Then it's a function of N, Dr. Rafiq, yes or no?
In this case, in the model of Dr. Bushra, is free of N, but I think that in social network, social graph, P must depends on N, logically. But in her model, it is free of N.
Then it's assumption, no, not really.
Yes, yes.
Yeah, I think it's assumption, yeah.
Yes.
Second question, Doctor, about your choice of estimation, maximum likelihood. We know that maximum likelihood in many cases it's based estimator. We can choose other estimator. Why you have to choose this method?
Which method?
Why you have used the maximum likelihood estimator? P had the maximum likelihood estimator of P and not other estimators.
Because we have the BDF function, the multivariate normal distribution. So we try to find the maximum likelihood estimation of it.
But you have all condition that is consistent and based. Have you all these properties to use it or not?
You mean these three equations?
Yes.
Is P hat consistent? Is P hat converges in probability to P, for example? The asymptotic properties of P hat, it is the same question for me. Is P hat is consistent or not? Consistent, that means that it converges in probability to P, for example. Okay.
I'm not sure.
No problem.
Okay.
Thank you.
Thank you for you, Dr. Nish.
Thank you.
Other questions, please? Okay. And why you have your condition is that NP is more than 10? Why 10? Why not 9 or 11 or 12? Why 10? Why necessarily 10? Yes, this is here.
Yeah. It's based on the results we get here from these tables. We do the test many times for various values of P and N, and these are the values of N we get. So all of the 4 tables show if we multiply N times P, and when N times P is greater than 10, we get the P value becomes better, and the rejection proportion also. So
Okay.
this is
Yes. I don't understand. Sorry. Yeah. Okay.
Yeah, this is approximately based on the computations, not theoretical approve.
Okay. What do you mean by rejection proportion of simulated graphs?
So we do the test of chi-squared, for example, 1,000 times for 1,000 simulated graphs, and we see if we reject the hypothesis or not. So we want to reject only 5%, which is the level of significance we use in the test.
What is your hypothesis here?
If the joint degrees follow multivariate normal or not.
Okay. Are there other questions, please? The last question for me, how you can simulate a random graph?
There is a functions in R for some famous models like Erdős-Rényi. So you can just use the function and put your parameters. It is an iGraph package.
Okay. Are there other questions, please?
What are the real life applications by using this method in graph theory?
You use the Erdős-Rényi model.
I mean to say, whenever we study graph theory, there is a specific purpose. Like I study chemical graphs. It means my purpose is to find the computational work which will tell us about the entropy of the molecule, complexity of the structure. It will tell us about the melting points, boiling points, and like this type of results. It means whatever you have done in your work, what is a real life application where we can use it in real life?
Actually, the Erdős-Rényi model is the simplest random graph model.
Random graphs.
Yeah, it is very simple, and it does not capture the real world networks. There are other models like Watts-Strogatz model. This is to capture the properties of models that have small world structures. So Erdős-Rényi is good to study random graphs and the properties, main properties of random graphs, but it is not good to capture the structure of real world networks.
Okay, thank you.
Welcome.
Thank you, Dr. Muhammad, for your questions. Some other questions, please? If not, we have to thank again Dr. Bushra.
Thank you very much.
You have a question, Dr. Farhat?
Yes, one last question.
Okay.
I'm still stuck with this slide where you say we have to ignore the terms. Can you please move to that slide? When n goes large, you said we have to ignore p cubed.
Here?
Yes, this one. So in equation 4, you are saying for large n, we ignore the term 2p cubed. So it means the behavior of the p is actually important. So p cube is ignoring p cube means like p may have a very small value. So it means when n goes large, the p-value is also going to 0 when it's cubed. But what
Yeah.
about p square, which is a very close term to p as well? So how can you distinguish between a p cube and p square, where both p are probabilities of something?
Because so yeah, here if we just want to solve it for the quadratic equation, so we don't remove all the unnecessary terms. Here we want to remove only the cubic terms, and here we remove all the necessary terms, which is minus 4p squared.
Okay, thank you.
I think that we can do better, that we can obtain a refined expression of P than in equation 5 by studying the function fp equals 2p cube plus.
But all of these equations can be approximated to this ratio, sigma xi divided by n times n minus 1.
This term that goes to 0? This
No.
term?
You mean the ratio here?
Yes.
Sigma xi divided by n times n minus 1?
It not goes to 0?
No.
Okay.
Thank you very much.
Other questions, please? Okay. We have to thank again Dr. Bushra for this nice talk. Thank you also to the public and for all the questions. See you next week with Dr. Stefan Wagner from Australia, who gives us a talk. Will give a talk titled "Local Limits of Descent Bayesian Permutation and Trees." Thank you again, and see you next week.